Hello and welcome to the last lecture of the lecture series on low power circuits and systems. In this lecture I shall give an overview of the entire course. In other words, it will give a summary of the various topics that I have covered in this particular lecture series. You may recall that first I addressed the question why low power, why at all low power circuits and systems are necessary. And we know that there are various reasons. Number one is packaging and cooling cost. If the circuit is not designed for low power, the power dissipation is high. So, the packaging and cooling cost of the chip is higher. So, to reduce the packaging and cooling cost, it is essential to go for low power design. So, this is one reason. Second is, as you know, as the device size is shrinking because of the advancement of VLSI technology, the power density of the VLSI chip is increasing. That means, the amount of power that is being dissipated per unit area, that is increasing. That leads to what is known as hotspot. So, to avoid that, to reduce the increasing low power density, it is also necessary to go for low power design. So that the power density is not very high and no hotspot is developed. Then another reason is the use of VLSI circuits in portable systems. As you know, there is a proliferation of portable systems, portable battery operated systems in the form of laptops, cell phones, PDAs and so on. So, for these devices, as you know, they are running from battery. So, battery life is the important criteria which decides its sellability and if the power dissipation is not low, then you cannot really sell these products. So, for portable systems, low power is extremely important. Then reliability. It has been found that the power dissipation is directly related to low power, and it has been observed that every 10° increase in temperature, 10° centigrade increase in temperature reduces the reliability by half. By 50%. So, you can see why the low power is important. For reliable operation of the circuit, is it necessary to go for low power design, so that the temperature within the core of the chip is not very high. Then coming to the environment, as you know, as the processors are dissipating power, that power is ultimately discharged to the environment. So, it is leads to ultimately leads to global warming. So, it has strong impact on the environment. That is the reason, another reason why it is necessary to go for low power. And as a consequence, there is a changing trend. Earlier whenever the chip design is considered, then area and delay were the two parameters which were considered for the design of a circuit. But in addition to area and delay, another factor is now has become very important, that is your power. That means, in the present day VLSI chip design, apart from area and delay of the circuit, it is essential to have low power. That means, power has become another important design criteria. So, these are the various reasons why low power is important in VLSI circuits. Now, let us see how we can really go for low power. to design circuits by using low power, I mean to have low power, it is essential to identify the sources of power dissipation. I mean only then we can go for reducing the power dissipation or go for design for low power. So, as we know, the power dissipation can be broadly divided into two types: dynamic power. Dynamic power is the power dissipation when the circuit is in operation. That means input is changing, clock is applied to it, output is changing. In such a case, whatever is the power dissipation, that is known as dynamic power. And dynamic power has got three components: switching power, short circuit power and glitching power. I have already discussed in detail what do we really mean by switching power. Switching power is essentially used for charging and discharging the capacitors, various capacitors that is present within the circuit. So, as you charge a capacitor, then there is some power dissipation in these transistors, and also whenever you discharge, then there is power dissipation. Then short circuit power dissipation is whenever in the middle part of the voltage, when the supply voltage input voltage is less than VDD by VT and greater than the threshold voltage of the PMOS transistor, then there is the NMOS and PMOS transistors are shorted. That means you have got two transistors in series. This is the simple inverter. Both the transistors turn on for the input voltage range, for certain input voltage range, and during that there is a sorting between the VDD and ground, and this is known as the short circuit power. And glitching power dissipation occurs because there are undesired transitions within the circuit because of the delay. Ideally, the gates should not have any delay, but unfortunately there is finite delay of the gates, and that delay leads to power dissipation, leads to glitches. And whenever glitch occurs, undesired transitions like this type of spikes occurs, they lead to power dissipation. That means again for charging, whenever it goes from 0 to VDD, and again and also power dissipation occurs when the glitch signal goes from VDD to ground. So, this is glitching power dissipation. Then there is static power dissipation when the circuit is in standby. Normally, as we know, we assume that when the circuit is in standby there is no power dissipation, but unfortunately that is not true in deep submicron circuits, because there is still power dissipation because of leakage currents, and there are different types of leakage currents like diode leakage current, subthreshold leakage current and gate leakage current, which I have discussed in detail. And these leakage currents lead to power dissipation even when the circuit is not in operation. That means it is in the standby conditions. So, when the circuit is operation, both dynamic power and static power dissipation occurs. On the other hand, when the circuit is in standby condition, not in operation, then static power dissipation occurs. Okay. So, these are the sources of power dissipation. Now, let us see how we can really identify what are the degrees of freedom inherent in low power design space. So, various sources of power dissipation we have discussed. Now, on what parameters these power dissipations depend, that we have identified and discussed in detail, and we have seen that the power dissipation is dependent on these parameters like supply voltage, physical capacitance, switching activity. These three are responsible for that switching power dissipation. As we know that power dissipation is proportional to alpha, CL, VDD square and F. So, alpha is the switching activity, VDD is the supply voltage, CL is the physical capacitance and F is the frequency of operation. So, these are the parameters which we can control to reduce the dynamic power. On the other hand, for reducing the leakage power. Threshold voltage is the key parameter which can be controlled to reduce the leakage power, that is your when the circuit is in standby condition. So, these are the parameters which we can control, and based on this we have categorized various low power design approaches, and these can be categorized into three types. Number one is minimizing switch capacitance, minimizing leakage power, and supply voltage scaling. So, these are the three categories which have been discussed in detail in this lecture series, and I shall try to give an overview of these techniques in this lecture. Now, as we have seen, supply voltage is the most important parameter, because there is a square law, dependence, VDD square is proportional to power dissipation. So, supply voltage has a strong dependence on power dissipation, and that is the reason why supply voltage is very important, and reduction in supply voltage is used to reduce the power dissipation. Now, there is a big challenge whenever you use supply voltage scaling for reducing power dissipation. Indeed, there is a factor of 2 reduction in supply voltage yields a factor of 4 decrease in energy. Unfortunately, as the supply voltage is lowered, delay increases. As you can see in this curve, the normalized energy is plotted against the supply voltage. As the supply voltage is reduced from 5 volt to 1 volt, we can see how the energy is getting reduced, energy dissipation is getting reduced. Unfortunately, as we do so, we find that as the supply voltage is reduced from 5 volt to 1 volt, the delay is increasing sharply. So, what it means? It means that we can reduce the power dissipation by reducing the supply voltage, but that leads to increase in delay. In other words, performance degrades. So, the challenge is we shall reduce the power dissipation without compromising performance. That is the challenge. So, objective of supply voltage scaling is to scale supply voltage without compromising performance. That is the basic idea of supply voltage scaling techniques used for achieving low power. Now, we shall consider various voltage scaling approaches. They can be categorized into 4 different types. Now, first one is known as static voltage scaling. So, in case of static voltage scaling, different blocks or subsystems are given different fixed voltages. That means, what is being done, the entire circuit is divided into different voltage domains, say 3 different voltage domains, and this is applied one voltage may be 1.5, this is given say 1.1, this may be given 0.8. So, these voltages are given to different parts of the circuits. So, that means, this is one voltage domain, this is another voltage domain, this is another voltage domain. So, these 3 voltage domains are identified, which will operate in such a way that the performance will not be degraded, but they will operate in different voltages and which are fixed, and this is done at the time of design. So, this is known as static voltage scaling, SVS. Then your multi-level voltage scaling, MVS, this is an extension of SVS, that is static voltage scaling, where the supply voltage is switched between 2 or few fixed voltages. Here in your static voltage scaling, we have assumed that these voltages are fixed, but what can be done in MVS? This can be made 1.5 volt at some point of time, at some other point of time it can be made 0.8 volt, or this voltage can be made 0.8 volt at some other point of time. That means, at different time instances the different blocks of the circuits are given different supply voltages, that is your multi-level voltage scaling. So, switch between two or few, note this, the number of such voltages is very few, maybe 2 or 3 or 4, not more than that. Then comes the dynamic voltage and frequency scaling, where which is an extension of the multi-level voltage scaling, where a large number of voltage levels are dynamically applied for different workloads. So, this particular technique is based on the monitoring of the workload of the processor, and as the workload changes, the voltage and frequency. So, we can say Vi and Fi a pair. This pair is kept on changing depending on the workload. Why both are changed? Because as we know, as we reduce the supply voltage, you have to reduce the frequency of operation as well, because for as you reduce the supply voltage, the delay increases. So, it will operate lower voltage. So, that is the reason why as you go from one workload to another workload, you will change from Vi Fi to maybe Vj Fj. So, this is another pair. So, this is known as dynamic voltage and frequency scaling, and in this particular case you have got a large number of voltage frequency pair, not few as was done in case of multi-level voltage scaling. Then finally, you have got adaptive voltage scaling, AVS. This is an extension of the dynamic voltage and frequency scaling, where a control loop is used to adjust voltage and frequency for changing workload. So, the other three approaches are identified at design time. That means, based on the analysis of the static timing analysis of the circuit, it is identified at what voltage it should operate at what frequency and so on, and that is how, depending on the workload, the voltage and frequency pairs are identified. Now, whenever the circuit is running in working condition, that time the environment is not known at design time. That means, it can operate at different temperature, and because of that the voltage and frequency requirement can be different, and that is the reason why in adapted voltage scaling the voltage actually it is a closed loop technique. Whatever voltage is required that is identified, and frequency of operation that is required for that voltage to sustain that workload is identified at run time. So, you have an additional hardware which finds out the voltage and frequency to be used in this circuit. So, adapted voltage scaling techniques require additional hardware to identify, to find out the voltage and frequency, and however, it gives you much better performance, much reduction in power dissipation, because it is done at run time. Now, so far as the static voltage scaling techniques are used, we have discussed two basic approaches. Now, first one is device feature size scaling. As we know, because of the advancement of technology, the feature size of the devices are decreasing. As the feature size of the devices are decreasing, the supply voltage is correspondingly reduced to achieve lower power dissipation. That is what is being done in your device feature size scaling. So, as you go from one technology generation to next technology generation, as the device size is reduced, the supply voltage is also reduced, that which leads to reduced dynamic power dissipation. Of course, as you reduce the feature size below 90 nanometer, then of course, you will see that the leakage power increases. So, although dynamic power dissipation decreases as you reduce the supply voltage, the leakage power increases. So, we have to use suitable technique to reduce the leakage power, and which can be done by controlling the threshold voltage, which I shall discuss, which we have discussed in detail. So, that is about device feature size scaling. Now, coming to architectural level approaches, we have discussed two techniques, parallelism and pipelining. Normally, as we know, parallelism is used to increase the performance. That means, instead of one processor, if we use two processor, then performance is doubled. But instead, that means, here in this case what we are doing, we are using parallelism for higher performance. But when our objective is not performance, but power, lowering the power dissipation, then what can be done? We can use parallelism for low power. That means, we use say more than multiple processors, but which will give you the same performance as the single processor. And then what can be done? The voltage and frequency of the processors can be reduced, and that will lead to reduced power dissipation. That means, this is essentially parallelism for low power. Similarly, as we know, pipelining is used again for improving the performance. Most of the modern processors are pipelined, and pipelining has been used to improve the performance. So, as we know, pipelining essentially dividing a task into a number of subtasks, then each subtask is performed in a overlapped manner. That is the basic idea of pipelining, as we have seen in details. Now, whenever we use pipelining, then there is a, since we are performing subtask, the clock frequency is increased. Clock frequency is increased for in pipeline system. That means, if the if you have got 5 stages, the clock frequency can be 5 times. So, 5 stages leads to clock frequency 5 into f. So, clock frequency is increased, and as a consequence we get the throughput increases by 5 times, performance increases. But instead of this, instead of increasing the clock frequency, if we do not increase the clock, instead of making it 5 f, if we keep the clock frequency same, then what can be done? For each of these stages, the supply voltage can be reduced, because clock frequency is reduced, delay is you can afford larger delay, and as a consequence the clock frequency is reduced. This will give you, and also the frequency is reduced. So, reduced voltage and frequency can be used whenever we go for pipelining for low power. So, this is the basic idea of pipelining for low power. So, these are the static voltage scaling approaches, and these are decided at design time, as I have mentioned. Then comes to multi-level voltage scaling, and here again the basic concept is high VDD gates have less delay, but higher dynamic and static power. What can be done? Voltage islands can be generated at different levels of granularity, such as macro level or standard cell level. So, what can be done? We can create islands of circuits which will have different levels of granularity, maybe macro level or standard cell level. Then each of these islands can operate at different voltages, and at different voltages at different instances of time, I mean different voltages that can be switched if necessary whenever the workload requirement is different, and total power consumption can be reduced without degrading the overall circuit performance. And whenever we go for multiple VDD circuits, there are a number of issues to be considered, and we have discussed all these issues in detail one after the other. Number one is voltage scaling interfaces. That means, whenever we are using say two such macros or modules and signal is going from one to another. In such a case we have to take appropriate action such that this output does not affect the performance, I mean operation of the circuit this way or the other way. So, sometimes we have to put additional hardware in the form of level converter. So, level converter needs to be used and converter placement is one of the important issues whenever we go for multiple VDD circuits. So, interfacing in the interface part we have to consider this converter placement, then floor planning, routing and placement, because different parts of the circuits will be operating in different voltages. So, they have to be placed properly, you have to make suitable floor planning, you have to do the routing not only of the signals, but also the supply voltage, and you have to place them properly. Then you have to also switch multiple supply voltages, say take different supply voltages and also along with the switches. For example, if this module is operating in multiple voltage switching, then you will require two voltages, say 1.1 volt or 0.8 volt, and you have to switch this voltage, and obviously this will require additional complexity, because you have to press the switch, you have to also multiple supply voltages are to be taken to different parts of this hardware, and you have to, and in this case the static timing analysis becomes very complex. So, when the entire circuit is operating at a single voltage, the static timing analysis, that means the delay of the circuit, can be very easily modeled and computed. However, whenever we are using multiple voltage levels and that too is changing with time, then static timing analysis becomes very difficult, and this static timing analysis is very important for reliable operation of the circuit, because what will be the delay for different supply voltage, that has to be identified. Then power up and power down sequencing is also very important, because the order in which powering up and powering down occurs, because sometimes as I have mentioned, you will be switching from say 0.8 to 1.1 or you will be switching down from 1.1 to 0.8. So, the how you will do that, in which order you will do, and whenever it is a complex circuit, we have got multiple voltage domains, this powering and powering down sequencing becomes a very important issue, and that has to be the sequencing has to be done properly for reliable and correct operation of the circuit. Then comes the question of clock distribution. We have seen that the circuits are operating at different voltages and frequencies. So, the clock has to be distributed, and if multiple clocks, I mean the different frequencies are to be applied, that also has to be distributed properly. So, these are the different issues to be considered whenever we go for multiple VDD circuits. Then another voltage scaling technique is your dynamic voltage and frequency scaling. So, which I have as I have already told, as the workload changes, as you can see, normally if we do not do voltage scaling, only the frequency changes, then linearly the energy reduces. However, whenever we go for reduction of voltage and frequency both, then this is how this will be the ideal dynamic voltage and frequency scaling curve, and as you can see, there is significant reduction compared to no voltage scaling. That means only frequency is reduced for different workload in this in this particular case, but here both voltage and frequency are reduced, leading to significant reduction in power dissipation. So, in this particular case, energy drawn can be reduced by dynamically adjusting both voltage and frequency that meets the workload condition, and we have already discussed about this formula, that power dissipation P is equal to C VDD square F, and I mean this plot gives you the idea about how it will how the power dissipation is reduced or energy normalized energy reduction take place. And this is the model of the dynamic voltage and frequency scaling system. As you can see here, this is the processor, variable voltage processor, which can operate at different voltage and frequencies. For the processor has been designed that way. Transmitters, Crusoe processor, or many other modern processors have been designed which can operate at different voltages and frequencies. And here you can see there is a workload monitor. So, the workload monitor based on the workload, it controls the supply voltage, that means the DC to DC voltage converter is there which receives a fixed voltage and generates different voltages. Similarly, you have got a frequency generator that controls the frequency. So, depending on the workload, voltage and frequency can be controlled. And as you can see, the inputs are coming from different sources, and there is a task queue, and operating system schedules the tasks to the processor, and accordingly the workload changes. So, and based on that workload, the voltage and frequency are controlled. So, workload for the next observation interval can be predicted by the operating system kernel based on workload statistics of the previous n intervals. So, it works in this way, that means based on the previous history, it identifies, it predicts the future workload, and based on that and voltage and frequency are identified, and that controls the circuit. So, as it is shown in this particular model. Okay. Now, coming to the adaptive voltage scaling, as I have told, the voltage scaling techniques discussed so far, that means the static voltage scaling, then your multi-level voltage scaling or dynamic voltage scaling. Here those were open loop in nature, that means voltage frequency pairs are determined at design time, keeping sufficient margin for guaranteed operation across the entire range of best and worst case process voltage and temperature. That means, best and worst variations of PVT, process voltage and temperature, it should operate, and as a consequence the design is very conservative, and whenever the design is very conservative, then we do not get I mean the reduction that we get is not very high. So, as the design needs to be conservative for successful operation, the actual benefit obtained is lesser than actually possible. So, this is what happens in those conventional designs. That is the reason why in adaptive voltage scaling a closed loop feedback system is implemented, where the voltage scaling power supply and delay sensing performance per monitor at execution time. So, at execution time the delay is sensed, what is the delay for a given applied voltage, and accordingly this on chip monitor not only checks the actual voltage developed, but also detects whether the silicon is slow, typical or fast, and the effect of temperature on the surrounding silicon. So, at run time this process voltage and temperature conditions, in that condition it does the monitoring, and it can identify it controls the voltage and frequency to optimize the reduction in power dissipation, and that is the reason why among the supply voltage scaling techniques, this adaptive voltage scaling gives you the best reduction in energy. However, it is much more complex, and you require on chip monitor, some extra hardware within the chip. Okay. Now, coming to minimizing switched capacitance, we have several approaches, and these approaches are mentioned and listed here. First one that we discussed is hardware software trade-off. As we know, same functionality can be realized either by using hardware or by purely by software or by a judicious combination of hardware and software. Now, which combination gives you best reduction in power dissipation, that is what is being done in software hardware trade-off. So, same functionality can be either realized by hardware or by software or by combination of both, and as we know hardware based approach is faster, costlier and consumes more power. On the other hand, software based approach is cheaper, slower and consumes lesser power. So, you have to partition, you have to identify which part you will realize by hardware and which part you will realize by software, and then you get best reduction in power dissipation. So, that is the hardware software trade-off. Then second technique that is used for reducing minimizing switch capacitance is bus encoding. We know that whenever we have got say more than one chip or processor, or maybe within a single chip you have got multiple cores or multiple subsystems, they are communicating with each other. Now, communicating data bits in an appropriately coded form can reduce switching activity. Now, as the signal is sent through the bus, communicated over the bus, you can do the coding, and there can be two, they can be done for two basic purposes. One purpose is remove undesired correlation among information bits, as you do in case of encryption. So, this is one goal. Another goal is introduce control correlation like spectrum shaping, timing recovery, which are used in spectrum shaping, timing recovery and error detection correction, where instead of removing undesired correlation, we are introducing correlation, and this bus encoding is a technique which belongs to this category and which we have discussed in detail, and the coding for reduced switching activity falls under the second category, which is being done, and we by introducing sample to sample correlation such that the total number of bit transitions is reduced. So, our objective is to reduce switching activity by suitable bus encoding, and there are various bus encoding techniques, and this is the basic scheme which is shown here. So, you have got a sender which does the encoding. So, n bit is converted into m bit, and there is a decoder at the other end which again converts m bit to n bit, and here is the receiver. So, they can be categorized into redundant, non-redundant, one to one, one to many, and one to where your encoder with memory and decoder is memoryless. On the other hand, one to many can be encoder with memory and decoder memoryless. There are several techniques like gray coding, which I have discussed in detail, and then bus inversion encoding and T0 encoding. So, in gray coding we have seen it is a one to one coding, and it does not require any memory. On the other hand, bus inversion coding is again one to one coding, but it requires memory in the circuit. And then T0 encoding, zero transition, called zero transition encoding, there also memory is required, and these three encoding techniques we have discussed in detail, and which can be used for bus encoding. Okay. So, apart from bus encoding, we can use another technique to reduce the power dissipation is clock gating. So, this clock gate, a major component of processor power is the clock power. Clock has to be distributed throughout the chip, and clock will control the transitions of different gates. So, clock gating can be done to reduce the dynamic power, and one of the most common and widely used low power technique is clock gating. So, it is based on the observation that a large number of transitions are not necessary. So, such transitions can be suppressed without affecting the functionality. So, here many transitions are taking place within the circuit because you have applied the clock to it, and those transitions are unnecessary, and when the transitions are occurring, power dissipation is occurring. So, if transitions can be suppressed by clock gating, there will be reduction in dynamic power dissipation. That is the basic idea of clock gating, and which I have discussed in detail, and here is the basic idea. Use of a functional element is highly dependent on the application in hand. So, there are opportunities to sort of circuits that are not in use. So, when it is not in use, clock can be gated. So, dynamically preventing the clock from propagating to some parts of the circuit under certain conditions. So, you have to identify the conditions, and when the conditions are satisfied, then the clock is gated. As you can see, when clock is not gated, then you have got dynamic power dissipation as well as leakage power dissipation. However, when clock is gated, you have got only leakage power dissipation, not the dynamic power dissipation. So, therefore, there is significant reduction in power dissipation that will take place whenever clock gating is done, and we have discussed how you can really achieve clock gating in different parts of the circuit. And the clock gating can be done with different levels of granularity. Granularity of the circuit block at which clock gating is applied greatly affects the power savings that can be achieved. So, if the gating, if you get larger block, then there is a larger power saving that will take place, but you will get fewer opportunities to do so. So, that is the reason why there is 3 levels of granularity: module level clock gating, resistor level clock gating, and cell level clock gating. So, whenever you go for module level clock gating, so for whenever you are able to do the gating, there is a significant saving, but this cannot take place very frequently. On the other hand, whenever we go for cell level clock gating, this gating can be done more frequently. However, whenever you do the gating, saving in power is not much, a small saving in power. So, depending on the application, depending on the nature of the circuit, you can go for these 3 types of clock gating. Not only clock gating can be done in combinational circuits, the finite state machines can also be gated. So, can be clock gated. So, here this is known as gated clock finite state machine. So, here as you can see, normally this is the schematic diagram of a finite state machine, and directly clock is applied here, and the sequential circuits operates, finite state machine operates. However, what has been done here? Here you have got a circuit FCG which identifies when clock can be gated for this finite state machine, and then it does not allow this clock to be applied to this circuit whenever gating is, transitions are not necessary. So, for Moore machine, a self loop corresponds to the ideal condition. So, in this ideal condition, clock can be stopped. That means, in this case the output will not change for the input combination, state will change. So, those conditions can be identified by FCG, and accordingly the clock gating is being done in gated clock finite state machine, and I have discussed it in detail in this lecture series how finite state machines can be clock gated. Apart from clock gating the finite state machine, you can do finite state encoding. As you know, whenever you realize a finite state machine which has got different states, and each of these states are to be encoded. So, state encoding is usually done to reduce the area of the circuit. Traditionally that is what is being done, but that whenever you do the state assignment strongly influences the complexity of the combinational part of the circuits, which affects the area and delay. However, now what you are trying to do, the state encoding is being done, which will reduce the switching activity for the reduction of the dynamic power. So, an objective function gamma is minimized, where gamma is equal to summation of Pij into Wij for all transitions, where Pij is the probability transition from state Si to state Sj, and Wij corresponds to weight corresponding to the activity factor. Here the basic idea is, as we go from one state to another state, there is a transition, I mean there is a bit transition. Now, we have to minimize the bit transitions such that when the finite state machine is operating, the power dissipation is reduced. So, that is what is being represented by this objective function, and state encoding can be done to reduce the switching activity apart from, I mean, area and delay. Now, we have discussed about different types of logic styles that can be used to realize CMOS circuits. So, essentially, as I have already mentioned, our entire course is oriented towards CMOS circuit, which is the technology of the day, and you can use I mean different types of CMOS circuits. One is your static CMOS circuit, which is conventionally used, then another is dynamic CMOS circuit, another is pass transistor logic circuits. So, although static CMOS circuit logic is the most popular, but they require I mean a much higher logic circuit. I mean the number of transistors is much larger in static CMOS circuits, and the number of transistors can be reduced in dynamic CMOS circuits and also in pass transistor logic circuits. So, instead of realizing circuits by using static CMOS circuits, if other alternatives are used, then there is a possibility of reducing the power dissipation and save energy in realizing the same functionality. So, or another alternative is you can make a judicious combination of static CMOS circuit and dynamic CMOS circuit, or static CMOS circuit and pass transistor logic circuit to realize different functionalities leading to overall reduction in power dissipation. So, logic styles is one of the important area. Now, coming to the leakage power, we have so far we have discussed techniques about the reduction of dynamic power. Now, the leakage power reduction techniques can be broadly divided into two categories. Number one is standby leakage reduction techniques and runtime leakage reduction techniques. So, under the standby leakage reduction techniques, we have discussed various approaches like transistor stacking, variable threshold voltage CMOS, VTCMOS, then multi threshold voltage CMOS, power gating, and dynamic VDD scaling. So, these are coming under standby leakage reduction techniques. Then you can go for runtime leakage reduction techniques. That means, standby leakage reduction techniques can be used when the circuit is in the standby condition, that means the circuit is not in use. On the other hand, this runtime leakage reduction techniques can be used even when the circuit is in operation. Earlier, since the dynamic power was a significant component, much larger compared to the static power, standby I mean the leakage power reduction was mainly focused for for standby reduction. That means, these techniques were used, standby leakage reduction. However, nowadays in deep submicron technology, the leakage component is comparable, has become comparable to dynamic power when the circuit is in operation. So, runtime leakage reduction has become important in the deep submicron technology or present day technology. So, and for that purpose you can use different techniques like dynamic VTH assignment approach or dynamic VTH scaling, which is also known as VTH hopping. So, these techniques can be used. Let me very quickly give an overview of these techniques. As I mentioned, the key parameter that is used for leakage power reduction is the threshold voltage VT, and here as you can see, as the supply voltage voltage is scaled down to reduce power dissipation, the threshold voltage is also scaled down to maintain performance. So, that means the threshold voltage has strong dependence on the leakage power as well as on the delay. So, we can see that normalized that threshold voltage, if it is reduced, delay reduces, but the subthreshold leakage increases. So, we have to optimize the realization design in such a way that threshold voltage is properly adjusted or controlled such that we get overall reduction in leakage power. As I told, this is one of the standby leakage power reduction technique, that is your transistor stacking. So, here it has been found that, so this is a 4 input NAND gate, static CMOS NAND gate. Here it has been found that if the number of transistors that is in series, if more, I mean if we have got more number of transistors off which are in series or which are in stack, then the leakage power is reduced, which is known as stack effect. So, this is known as transistor stacking, and we can use this stack effect to reduce the power dissipation in this way. Then we can use the VTCMOS approach, where as I have already mentioned, we control the threshold voltage dynamically. I mean when the circuit is in operation, threshold voltage is lower by adjusting the body bias, and when the circuit is in standby, the threshold voltage is made higher by adjusting the body bias. and as you can see, for every 100 millivolt increase in threshold voltage, the subthreshold leakage current reduces by half. So, VTCMOS approach is used in this way for reducing the leakage power by adjusting the body bias to control the threshold voltage in active and standby mode. And power gating can be done which is known as empty CMOS. Again, you have got two modes, active mode and low power mode, and in active mode your performance is better, and in low power mode there is a significant reduction in power dissipation. And this approach, power gating approach, is more invasive than clock gating, because that interblock interface communication, it affects the interblock interface communication, it is more invasive, and it adds significant time delays to safely enter and exit power gated modes. So, power gating is very complex, and it involves a number of issues like at what granularity level it is being done, what is the topology of the circuit, what is the impact of power gating on the classes of subsystems. Then you have to design the switching fabric, you have to use isolation strategy, we have to use retention strategy. When the circuit is in standby, you have to retain some of the states, and that retention strategy has to be identified. Then power gating controller circuit has to be designed. So, these are the techniques which I have discussed in detail in this lecture series. Then coming to the adiabatic circuits, so far we have seen that circuit is operating at full swing voltage. That means, circuit operates at full supply voltage VDD, it does not operate at any other intermediate voltage. Now, in adiabatic, and whenever this is being done, the lower limit of that switching power dissipation, lower limit is CL VDD square part 2 by 2 part transitions. Can we go can we still lower this power dissipation? And that can be done by in adiabatic circuits. The switching power dissipation is achieved, which is below this limit. And actually the term adiabatic is referred to thermodynamic processes that exchange no heat with the environment, and this reduction of power dissipation occurs at the cost of slower speed of operation. And also in adiabatic circuits, this recycling of energy can be achieved, which I have discussed in detail in this lecture series. So, here as we shall see, the adiabatic circuits can operate at a when the delay is large. So, adiabatic circuits are slow in today's standards. So, it requires about 50% more area than the static CMOS circuit design, and circuits are relatively complicated, and however, you can identify applications where adiabatic techniques can outperform conventional ones. Okay. So, adiabatic circuits are used, are not very popular nowadays, but it may become popular in future. So, we have to identify applications where they can be used. Coming to the last topic, that is your battery driven system design. We have, as I have already mentioned, there is proliferation of portable computing and communication equipment such as laptops, palm top and cell phones is taking place, and they are battery operated. And growth rate of this portable equipment is very high compared to servers, desktops, workstations, and complexity of these devices is also increasing. So, as these devices are battery operated, battery life is of primary concern. Unfortunately, the battery technology has not kept up with the energy requirement of the portable equipment. So, we have discussed techniques for battery driven system design, and we can use low power design methodology to make the products battery operated systems more viable, more commercially viable. And you can use different techniques like frequency scaling, supply voltage scaling, dynamic power management, battery aware task scheduling in battery driven system design, and particularly what is being done to basic idea objective is to maximize the battery lifetime by exploiting the characteristics of the battery, and these are the three important characteristics which are exploited. Number one is rate capacity effect. A higher rate of discharge leads to lower available capacity. Recovery effect, the battery whenever it is kept in idle condition, the battery charge recovers. So, battery voltage recovery occurs, and non increasing profile, non increasing load sequence leads to lesser drop in voltage. So, by exploiting the important characteristics of the batteries, we are using battery aware task scheduling to reduce power dissipation. Finally, we have discussed about variation tolerant design. Basic idea is this, in earlier designs the variations were not much, but in present day technology the important parameters like threshold voltage, which varies over a range, you cannot consider as a fixed. So, it is a statistical parameter. So, it is necessary to use statistical CAD tool, so that the circuit can be variation tolerant. That means, circuit will operate even when the threshold voltage and other important parameters vary over certain range. So, this we have discussed in detail in this lecture. So, with this we can we have come to the conclusion of this lecture, and we have summarized and given an overview of the entire lecture series. Thank you.